Okay, what I'm going to try to do here is use Desmos to try to walk our way through going through Newton's method one whole time. This is a typical kind of example. We have two different functions. We want to find out where they intersect. If I just turn the functions on, you can see there's ln of x. You can see there's e to the minus 0.5x. I'm just going to write down the equation that we would normally have to solve. I would write down the ln of x equals e to the minus 0.5x. And we're going to see that we can't do that algebraically. If I try to take the ln of both sides, the right side turns out nice, the left side sucks. It's got ln of x. If I e to both sides, the left hand side is not nice, I get x, but now that I have e to the. Solving this algebraically is not possible. And so what we want to do is solve it numerically, and the best way to do that is Newton's method. I'm going to go over to our statement about how to run through Newton's method. The very opening line says, estimating solutions to f of x equals 0. So we're not supposed to be setting two equations equal to each other. We're supposed to be solving an equation of the form f of x equals 0. So I'm going to come over here, and I'm going to invent a new function. I'm just going to call it f of x, and I'm going to just take ln of x minus e to the minus 0.5x like that. Let's see here. I want to go back to my normal thing here. Just slide this over a bit. Now remember, we were looking for, let's say, where the green function, hits the red function. Yeah, I like that better. So we're looking for the x-coordinate where the green function and the red function hit. You can see that's exactly the same x value where the blue function hits 0. So that's actually what we're going to do. So we're not going to worry about the two original functions. I'll shut them both off. And all we're going to do is trying to find the place where the blue function crosses the x-axis. Now in practice, we're not just allowed to say the graph, oh, there's the graph. I can see where it crosses the x-axis. The usual practice of doing this, because we'll only have data or some horrible other examples like in differential equations, what we want to do is show that there's a solution. The way that's usually done is find a place where x, when you plug in f of x, you get 0, that's something negative. And when you pick another number and plug it in, you get something positive. That's very easy with Desmos. I think it's easier to do than what I just said. I'm just going to make a little tiny table. I'm just going to go like this. All right, so what I want to do is instead of having y1, I'm just going to have f of x1 like that. And I'm going to look at the graph, and I'm going to plug in 1, and I see the answer is negative. I plug in 2, I see the answer is positive. Since this function is continuous, and it's negative here and positive here, there's got to be some place in the middle where it's 0. That's usually as hard as it gets, of at least establishing that there's a solution. Now I'm going to run back over to Newton's method. We're now done with step 1. With step 2, it says even if we can't solve the equation algebraically, we could still make a reasonably close guess. And we don't care that it's that close. We do care that it's easy. So I'm going to come over here, and I see, for example, that where the blue line crosses the x-axis, it's pretty close to 2. So what I'm going to do is I'm going to come over here, and we always call our reasonably close first guess x0. So I'm going to go like this, and just say it's 2, like that. That shouldn't kill us too much. All right, so we've actually found our reasonably close guess. Now, what does the procedure say? It says what we want to do is set a tangent line equal to 0 and solve, because that's going to be easy. That does mean we're going to need a tangent line. Now, what am I going to do? I'm going to find the tangent line at the reasonably close guess. Let's find it first. We'll see what happens, and then we'll try to explain what's going on. Meanwhile, I want to find the equation of the tangent line to this graph at 2. I'm going to need the derivative, so I take the derivative. I'm just going to write down f prime of x equals 1 over x, like that, plus 0.5 e to the minus 0.5x, like that. Now what am I going to need? I'm going to remind ourselves what the formula for the tangent line is. It's L of x equals f of a plus f prime of a times x minus a. In this case, a is 2. So I'm going to need f of 2. We already have that, but I want it down here. We're also going to need f prime of 2. So I'm going to write that right like this. And now we need the equation of the tangent line. And I'm just going to plug this in. I haven't tried copying and pasting. That would make life easier if I could do this. So I'm just going to see if I can come over and copy this number right here and put it right here. Turn it into a dollar sign. Yeah, that's not good. All right. And then I want plus, and I want this line, this thing right here. I'm going to paste it right here. This is going to be our slope. You didn't give me dollar signs that time. Times x minus 2. And you can see that's the equation of the tangent line that we want. Now, let's talk about what we're going to do next, why graphically it looks like it's right, and then we'll try to argue why it would always be right. I'm going to zoom in a bit so we can actually get our original stuff on here one more time. Yeah. Okay, here we go. Remember, we're looking for where the blue line crosses the x-axis. Originally, we said, hey, 2's pretty close to where that graph crosses the x-axis. You can see that this distance is still actually pretty far. So this is what we're going to do. We are going to set, instead of setting the blue curve equal to 0, which is impossible, we're going to set the tangent line equal to 0 and solve the linear equation, which is always easy. What we're going to get is where the red line crosses the x-axis. You can see that's actually very close to where the blue curve crosses the x-axis, and we should get a good answer that way. So we're going to do that. I'm going to do this the way they usually do this. I'm going to add myself a little note here. Hopefully you'll be able to see this later. And we're going to solve L of x equals 0, and we're going to do this in our heads first. If I take this equation and set it equal to 0, how do I do that? I'm going to subtract this negative 0.325 mess from both sides. I'm going to divide both sides by this 0.683 mess, and then when I'm all done, I'm going to add 2. And what I'd like to do is call the answer, it's not x naught, it is our next x, so I'm going to call it x1. And here we go. It's going to be minus 0.325267739 hope I did that right, divided by 0.683939720.586 to get out from under, and then add 2. And then add 2. And you can see what I get here is 1.524 blah blah blah. But that's where the red line crosses, which is very close to where the blue line crosses. The idea is we started with a reasonable guess that wasn't that close. We found the equation of the tangent line, which wasn't that bad. The only thing that makes this bad is the decimal places. And then we set the line equal to 0, doing the procedure basically in our head, and we came up with a new number. Now, how much better is this new number? Well, the idea is we want a number that when we plug in, we get 0. Our initial guess was 2. And when we plugged in 2, we got 0.325 something. That's sort of close to 0. It's not that close. We now have a new number where the red line crosses the x-axis. And when I plug that number in, so this is 1.524,435,078,71. Yeah, that's it. I get that. Now, what did I want to get? I wanted to get 0. Did I get 0? I did not, right? How much closer did it get to 0 than my original first guess? It's literally 10 times closer to 0 than my original first guess. So this 1.52 blah, blah, blah is a much, much, much better estimate to the actual solution than 2 was. That it almost always works as well. After we get very comfortable with it, we'll look at a few places where it can fail and why it can fail. But meanwhile, I'm told that every search with Google starts with something like this. So it's an important thing. Meanwhile, here's the really cool thing. We could do this again. Do the whole procedure again. Well, how am I supposed to do that? Well, the only thing we did is we found a reasonable guess, found the tangent line, set the tangent line equal to 0. But what we now saw is that 1.524,435,078,71 is a much more reasonable first guess than 2 is. So what I want you to do is your turn is just go through this whole procedure again, finding the tangent line at 1.52 blah, 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 setting that tangent line equal to 0, and coming up with a much better guess. Show me what's going on with the pictures, and then check numerically that the answer actually got a whole lot better.